Okay, so this week though, I'm very happy to introduce to you Christine Regalla. She did her Bachelor of Science from Lehigh University, and then did her master's and PhD at Penn State. Afterwards, she did an assistant professorship at Hobart William Smith Colleges before going on to do an NSF postdoctoral fellowship at McGill University. After that, she did about a 4-year stint as assistant professor at Boston University before moving to Northern Arizona University, where she is today. So I'm really happy to have you today, and I'm going to hand it over to you.
All right, thank you so much, and thanks for the invitation to join your lecture series. So I'll go ahead and share my screen. And get my Zoom window open. Okay. And so what I wanted to talk to you about today is the results of a collaborative effort between myself and a number of colleagues from US academic institutes and the US Geologic Survey and Canadian institutes at the Pacific Geoscience Center and University of Victoria about understanding Forearc deformation in the northernmost part of the Cascadia subduction zone on the Vancouver Island region. So I'm going to start with this figure here on the right from the US Geologic Survey, which shows the plate tectonic setting. And here you see the Juan de Fuca plate subducting beneath the North American plate. And most of us are probably pretty familiar with the large megathrust earthquakes that have happened in the paleoseismic record on the Cascadia subduction interface, the magnitude 8s and 9s, and the future earthquakes that are impending. But there are also a network of faults in the overriding plate in North America, here shown by these red lines, that are active crustal faults that also produce a significant hazard to the regions around them, especially to population centers. They are, even though they are shorter strike length and can host smaller magnitude earthquakes, the amount of ground shaking, because they're closer to the surface and right near these population centers, can still be quite severe. And so ones that folks are probably pretty familiar with are the Seattle fault is one of the famous fault systems in this area. And what you might notice is that these network of red active faults exist in Washington state and project across to the US-Canada border, across the Strait of Georgia, but end before they cross into Canada. I always joke that they don't have their visa permissions to get into Canada. And so what we're trying to do is understand how the strain that we know is accommodated in the central and southern part of the Cascadia Forearc is actually translated to the northern part of the Cascadia subduction system, and understand where these faults are, when have they hosted earthquakes in the past, and think about what are the potential drivers of deformation in this area. And so my talk today is going to have two parts. In the first part, we're going to talk about where are the active faults in the northern Cascadia Forearc, specifically on Vancouver Island. And in part two, we want to talk about what is driving deformation. And in particular, I want to investigate the relative roles of plate interface coupling versus kind of upper plate or background stress fields. Okay, so for part one, where are the active faults? This is a regional location map that's going to appear on several of our slides. So it's a zoom in of a part of the area I showed you before. There's Seattle and Vancouver for reference in the Olympic Mountains. And this is the southern part of Vancouver Island. And so our group has been focusing on trying to test where the active faults are and identify them. And we've been focusing on these faults here in red, the Leech River Fault, the San Juan Fault, the Elk Lake Fault, and the Beaufort Range Fault. And our approach has used a combination of superficial and bedrock mapping combined with paleoseismic trenching. And to get the timing of events, we're able to use radiocarbon dating of detrital charcoal in these offset deposits, and combining these with collaborators to do shallow geophysical surveys to understand the subsurface fault geometries. Okay, and so first I'll go over some kind of our general methods. In order to identify these faults, again, some of our key tools have been geomorphic and bedrock geologic mapping. And we've been doing this mapping to identify offset quaternary deposits and topographic scarps associated with ground surface rupturing earthquake events, and to identify geomorphic piercing points or linear features that are displaced across faults so that we can determine both the magnitude of slip, but also the kinematics. Are they thrust, normal, left lateral, right lateral, strike slip? And on Vancouver Island, unlike where I am now in Arizona, where you are in a lot of parts of Utah, it is very densely vegetated. It's a temperate rainforest. And so here's a picture of a portion of, I think it's Bainbridge Island, just west of Seattle, where there's some faults identified by the Washington State surveys. So this is an air photo imagery here. And oftentimes I'll show this to audiences and ask them to think about, if you looked at this, could you identify where the active fault is transecting the surface? And it's quite difficult to do this. And this has been a hindrance to even just identifying where the active faults are and where strain is being accommodated in this part of the forearc, because you basically have to, be walking across it in the field to be able to find it or know a priori where to look. And so airborne LiDAR has been a revolutionary tool, both in the United States and now in Canada, where laser scanners from aircraft shoot signals to the ground, and that signal returns off of trees, buildings, but just like if you were standing in a forest with a canopy and we're looking up at the light, some of the rays of sunlight would come down and still reach the forest floor. And so some of these returns hit the forest floor or hit the ground surface and return back to the sensor. And we use these last returns or these ground returns to basically see through the trees and map out the ground surface. And so here's an image on the right here now of the hill shaded LiDAR elevation model of this part of the island, where you can see now pretty clearly the topographic scarp associated with the Tojam fault, offsetting these series of linear drumlinoid glacially striated landforms. So these are examples of both the types of fault scarps and the linear features that we're trying to identify on Vancouver Island. Second, then we are using paleoseismic trenching, where we're excavating 1 to 2 meter deep wide, 10 to 20 meter long excavations across the active faults. First, to just test that the topographic scarps and the deformation that we're seeing are actually associated with active faults. Our work has been, kind of putting these faults on the map on Vancouver Island. But then once we can confirm that they are in fact active faults between our trenching and our mapping, we want to determine the kinematics of slip, looking for offset deposits that we can reconstruct, and determine the number and timing of slip events. And so this is just a photograph of me here in one of our trenches on the Leech River Fault, doing a trench review for a number of the Canadian academic and seismic hazard researchers in the area. And on the left here, I have to give a shout out to Walter Langer, who's our backhoe operator. You're going to see a theme here. There's trees, there's a lot of forest, and a lot of the photos you're going to see are of some of the most open places. But many of our, actually all of our trenches, except for one, are located up into the forest onto hill slopes. And these are not locations that are accessible through typical backhoes. And so Walter Langer has what's called a spider backhoe, where he actually takes off the front wheels of the spider and the backhoe, and literally like it's like climbing up the hill like Spider-Man style. It's kind of wild to navigate his way through the trees. Excellent backhoe operator, and the reason why we've been able to trench in some of these really challenging landscapes. Okay, so when we do excavate our trench, what is it that we're actually looking for in the paleoseismic trench? And so first, we're looking for evidence of faulted quaternary deposits. And we're looking for datable material to bracket earthquake timing. On Vancouver Island, we've had the most success using detrital charcoal in our deposits. And importantly, we're looking for deposits called colluvial wedges that constrain earthquake timing. And so those of you not familiar with this, there's a little schematic here on the right showing what these colluvial wedges are. So I apologize, there's no scope here, but this should be about a couple meters in vertical here. And so when we have a fault rupturing to the ground surface, we'll displace the ground surface and produce a relatively steep free face initially. But that soil and sediment is not gravitationally stable at that high angle and pretty quickly unravels, such that this material on the upper portion here is deposited down on the downthrown block and essentially degrades back to angle of repose. And so that ends up generating this wedge of colluvium, the colluvial wedge, that in most modern systems where we've observed this happens in days to weeks to months to years, maybe decades after the earthquake. And so it's the deposit that, if we can identify this in the trench, that most closely is associated with the timing of the earthquake event itself. And so if we can extract charcoal from the base of this wedge and charcoal from the unit that it buries, we can bracket the time of an individual earthquake. And if this process happens again, and we down drop this side again, we'll again expose a new free face, and it will unravel again, and we'll build a second wedge of colluvium. So identifying the number of wedges, these often vary soils and have internal sorting and stratigraphy that helps us identify those deposits, helps us determine both the number of events and the timing in the trench. So now I want to take you through some of the key results of some of the faults that we've been working on now for about the past 5 or 6 years or so. And so I'm going to start here in the south. We got Victoria again as our location point. Vancouver and Seattle's behind the map here. And I'm going to be focusing in on the Leech River Fault here in this yellow box. And there's a geologic map of the area of that same area in the yellow box shown here on the right. And so the Leech River Fault is shown here by the set of black and red lines. It is first formed in the Eocene as a subduction plate interface, actually, between Matosan basalts, Eocene Matosan basalts, and the overriding Regalla terrain. So the Matosan basalts are correlative to the Silesia terrain and Silex basalts in Oregon and Washington, for those of you familiar with that. And in the Regalla terrain here, these are largely the schists of the Leech River complex. And so that these black lines are these inherited older Eocene fault structures. But when we looked at the LiDAR elevation models for this area, all of the red lines are areas where we saw a topographic scarp that we suspected might be associated with active deformation. And we focused our mapping and paleoseismic trenching work on the eastern half of the Leech River Fault, in part because of its proximity to Victoria, which is the capital of British Columbia. And it's also located along a lot of the water reservoirs and hydroelectric dams in the area. So it was of the greatest hazard in the area. So my next slide is going to zoom in on this eastern part of the Leech River. And I'm going to talk about two trench sites that we have at sites T1 and T2. Okay, so here's now the strip map of the eastern part of the Leech River Fault. Again, our green basalts, which are underthrust under the brown schists in this area. That bedrock lithologic contact here is in black. And the red marks are locations where we see scarps, topographic scarps that we have mapped as associated with the active deformation. And in some places, it offsets these yellow quaternary deposits, including these striated drumlinoid features with arrows indicating them in blue. But one thing to note is that the location of these active fault traces is somewhat parallel to, but doesn't exactly reoccupy the inherited fault planes themselves. Okay, so next I'm going to zoom into some of the geomorphic evidence from these sites for recent activity. And so I'm going to show you a site here on the western part of this section. This is a hill-shaded LiDAR elevation model of the area. So to get you oriented, uphill is on the bottom part of this towards the south, and downhill is towards the north. And one thing you might notice is this network of, in this case, shadowed drainages, abandoned channels that drain off the flank of this hill slope and this conical mantle of colluvium on the hill slope. And they are cut by this more east-west trending topographic scarp that offsets both the interfluves and the channels. And this is one of the examples of the fault scarps that we map along the Leech River Fault. And we've surveyed some of the topography to determine the topographic displacement of the ground surface across this fault. And I'll help show you here two of those profiles. One here is on the interfluve, and the next one is on the channel. So this interfluve profile here in orange, again, we're going to start on the uphill and kind of walk our way downhill on this as we go on this plot here. So this is starting uphill, walking downhill, and then at the topographic scarp, the ground surface is displaced upward by about 6 meters in the vertical direction. And if we do that same exercise in the adjacent channel, walking downhill, the ground surface within the channel, these abandoned channels, is vertically displaced by about 3 meters as you move downhill. And so again, just this difference in the vertical separation, the displacement of the ground surface between these older interfluves and the channels that have to be younger than the interfluves because they're incised into the deposits. This difference is indicating to us that there is at least more than one earthquake at this site that produces differential amounts of offset in these geomorphic landforms of different ages. And so we excavated 2 paleoseismic trenches at this site, and I'm just going to show you some of the key results from one of them here. So we are going to show you the excavation across one of our interfluve sites here. And on the right is basically the geologic map or the trench log of the cross-section view of the trench wall of this trench here. And so the key parts here, north or downhill is on the left, and we see north side up displacement of our basement unit in here. Our basement unit in here is till. And so this till in gray is displaced across a sheared zone of shear till shown here in pink. And all of these red lines are a distributed network of faults and fractures associated with deformation away from the core shear zone. The other important thing here to note is that there are 3 colluvial wedges, C1, C2, and C3. And this is indicating to us that there are 3 events at this site, producing north side upslip on a vertical to north dipping fault. The charcoal that we collected from this site yielded radiocarbon ages that allowed us to perform OxCal models that help us constrain the timing of each of these events. And based on that modeling, the 3 events in this trench are constrained to being at about 9,000 to 8,000 years before present, about 2,000 years before present, and in the past 1.7 thousand years before present. So now we're going to move slightly east along the Leech River Fault to one of our second sites. Again, down here is a hill-shaded elevation model of this strand here. And the thing to call your attention to here is this topographic scarp that offsets bedrock and both quaternary deposits across several kilometers of the landscape. And we excavated, again, a series of paleoseismic trenches here, and I'm going to show you the results of one of them at this site here. And so now we've resumed here. Here's our larger elevation model and our location of the trench again. This is the view of the trench log of the side of the trench wall. And again, similar to our previous site, we're seeing north side up displacement of till being accommodated across a distributed shear zone with a couple of different main fault zones here indicated with pink. And at this site, we see 1 colluvial wedge. So again, similar to our other sites, we're seeing evidence for north side upslip on a vertical to north dipping fault. And we have evidence for 1 earthquake in this trench that occurred between 13 and 6,000 years before present. And I'll note that that timing overlaps with the age of the oldest event in our trenches farther to the west. Another really interesting outcome of this trench, this is work by one of our PhD students who's now finished, Nick Herthausen. He also mapped the floor of the trench. So this here is basically kind of the footprint looking down in map view now on the floor of the trench. And he mapped out this network of fault zones across both sides of the trench and across the floor to try and make this sort of map of basically what the fault zone looks like 1.5 meters to 2 meters below the surface. And he interpreted and mapped out this network of faults that he's interpreting as a Riedel shear network. And this network is consistent with accommodating a component of right lateral shear across here. And that interpretation is consistent with what we know about the regional stress field. There's maximum compressive stress orientations here shown by these black arrows that have been determined from earthquake bulkhead mechanisms. That if we place this fault zone in that system also suggests that there's a right lateral component of deformation at this site along the Leech River Fault. And these field data are consistent with some results by, again, PhD student Geology, who was looking at earthquake seismicity beneath the Leech River Fault. So GA did hypo-DD double difference relocations of earthquakes along the eastern portion of the Leech River Fault. So again, here's our reference map. The block diagram on the right is going to be showing you the area of this yellow box. So north on this, it's a rotated view, is actually to the right on this block. So we actually have this like oblique view looking in on the side of the Leech River Fault. And so he found clusters of earthquakes that occur along semi-planar features that define a zone of seismicity that projects up to the surface where we map these active fault strands along the Leech River Fault. And so our interpretation is that this seismicity is outlining the subsurface geometry of the active Leech River Fault. The earthquake focal mechanisms that he was finding within these earthquake clusters are consistent with both right lateral and thrust sense earthquakes. So again, it's consistent with the right lateral and compressive sort of kinematics that we are interpreting from our trench sites. Another thing to note here actually is the geometry of this inherited subduction zone interface that I was talking about, that contact between the green basalts and the brown Leech River schists earlier. That contact has been imaged by seismic reflection profiles across the island from a lithoprobe time. And that contact is shown here in this dashed line. So this is the inherited fault contact. And their interpretation suggests that that fault has a dip, a much more gentle dip of about 45 degrees or so beneath the ground surface, different than the zone of seismicity than we're identifying for the Leech River Fault. And so this might suggest that the active fault may not actually be entirely reoccupying this older inherited structure. Okay, so to summarize the key points for the Leech River Fault, we're finding evidence for right lateral transpression on a steeply north dipping fault zone. Our paleoseismic trenches indicate that there are up to 3 Holocene rupture events. And in terms of magnitude of displacement, I didn't go into that in the trench data, but each one has about 1 meter of slip per event. And so from a hazard standpoint, that sort of displacements and the length of the fault that we're mapping suggests that the Leech River Fault is capable of producing magnitude 6.5 or greater events. And that our mapping of the active fault and the geophysical imaging of fault planes in the subsurface suggests that the active fault appears to be located near an ancient shear zone at the surface, but may diverge at depth. Okay, so now we're going to move to one of the other faults in our system. We're going to go from the Leech River Fault up island to the Beaufort Range Fault. So our view here is now going to be in this yellow box, which is going to be down here. And so this is a exaggerated 3-dimensional view of the Beaufort Range mountain itself. And everywhere where there are these yellow arrows, we've identified, again, potentially fault-related topographic scarps from LiDAR DEMs. And this is ongoing work by my PhD student, Emerson Lynch. And so I think I'll show you a couple examples of what those fault scarps look like along the Beaufort Range Fault. And so at the northern site here, again, we have a hill-shaded elevation model, uphill or northeast on this side and downhill or southwest there. And the key thing to note here is that in blue, it's indicating these channels that appear to be right laterally sheared across a network of these east-west trending topographic scarps marked out in red. Similarly, if we go farther south, show you some examples here. In this area, this is another hill-shaded elevation model of some of the fault scarps on the southern end. Again, we've got this series of abandoned channels and intervening interfluves that are offset by a large network of topographic scarps. And if we look, zoom in on any one of these, this is kind of a very zoomed in version of the elevation model across one of these channels. But if you follow the deepest part or the foul leg of the channel, when it reaches the fault, it becomes displaced in a right lateral fashion across that fault scarp. And we see that pretty consistently in the LiDAR DEMs and very consistently in the field. And so here on the left is a beautiful field photo of the very well exposed fault scarp in the forest of Vancouver Island. But here, this white line, this dashed line here is again marking out the foul leg of a channel that then abruptly is terminated against an interfluve and is displaced about 1.5 meters laterally to the right before it picks up again, moving downhill. And so from some of the results of the field mapping and surveys of these offset geomorphic markers, these interfluves and channels in this area, is suggesting that the Beaufort Range Fault consists of a steep, near vertically dipping, northeastward dipping fault zone, and that there's a series of fault networks that are consistent with the development of flower structures, and that our kinematic observations from the field are indicating that these fault scarps are accommodating both right lateral and dip slip. The next thing that Emerson has done is actually use the topographic surveys from a total station of individual channels and individual foul legs that are displaced across the fault, and reconstructed the 3D displacement of those to determine slip vectors along fault planes. And so that's what's plotted on this stereo net here. All of these arcs are the geometries of fault planes surveyed. Again, multiple dips because we're working with some flower structures here. And all of these points are basically the slip vector connecting these offset piercing lines, and the arrows indicate the motion of the hanging wall. And again, these data are all showing us that there's this right lateral strike slip and vertical dip slip happening along these steeply northeast dipping faults. But we can also do a kinematic inversion of these data. So similar to what you might do if you have a population of slicken lines in a fault plane, we can now use these slip vectors and the fault plane orientations from the geomorphology to invert the set for the kinematics consistent with displacement along all of these. And we do this using one of Rick Allmendinger's programs called FaultKin. And that inversion produces a pseudo focal mechanism that best describes the displacement along the entire fault system that would be consistent with this set of fault geometries and slip senses. And what this is showing us is that the Beaufort Range Fault is in general accommodating right lateral transtension. with this range side down sort of motion. And although I don't have a lot of information about it here in this talk, one of the interesting things that we're hunting down here is one of the largest earthquakes to have occurred in Cascadia in historical times is the magnitude 7.2 Vancouver Island earthquake, whose epicenter is just off the page. And one of the nodal planes of that earthquake is basically parallel to what we are observing for our fault system, and has slip inversions that are similar to what we're seeing. And so this Beaufort Range fault may be a candidate fault for hosting it. That earthquake occurred, but the host fault has not been found. Okay, we've also done a paleoseismic trench across the Beaufort Range fault, again at this southern site, across one of the channels that's displaced by these topographic scarps. So again, here on the left is a simplified version of one of our trench logs, where now we have southwest or valley side motion up, displacing till across here. Sorry, the till is projecting beneath the ground surface here. So several meters of vertical displacement of till, again, across a pretty wide shear zone here shown in pink. And the key thing here is that at this site, there are 5 colluvial wedges that we've mapped, indicating there have been 5 earthquakes along this fault since the deglaciation of the valley. And our radiocarbon ages from these are indicating that those 5 earthquakes have been spanning the time period between about 13,000 years ago to the past couple hundred years. Okay, so to summarize our information on the Beaufort Range fault, both fault exposures and offset deposits indicate that there's right lateral oblique transtension being accommodated by the Beaufort Range fault along a steeply north dipping fault. And our paleoseismic trench and mapping data provide evidence for 5 surface rupturing earthquakes since about 13 to 8,000 years before present, each with about a meter of slip per event. That, combined with the strike length of our mapped fault, again is suggesting the Beaufort Range fault is capable of producing magnitude 6.5 or greater events. Okay, so moving on our tour of the island, we're going to come a little bit closer back again to Victoria here, to the Holoc Elk Lake fault, which is in the greater Victoria area, also near the airport, if folks are familiar with that part of town. The map on the right is going to be showing a part of this area here in the yellow box. So again, we've got a hill shaded digital elevation model from LiDAR of the area, and you can see here there's a streamlined drumlinoid feature that has a topographic scarp here indicated by these black arrows that transects across the landscape and projects into the lake. And we excavated a trench here along the lake shoreline, trying to access finer grain deposits rather than till across the glacial drumlinoid, which turned out to be a trenching adventure in and of itself, because we were trenching below the water table, so we had to pump the water out of our trench the whole time. So that's its own stories. But the trench itself here, I'm going to show you again one picture of one of the trench logs from one of the walls of this, shown here on the lower left. This is again showing south side up displacement of till, just ever slightly shown here, exposed in the trench log. Till is being thrust up over the till down here, along a moderate to steeply dipping thrust fault. And again, there's a series of faults here in the hanging wall that are subsidiary to that. But this thrust fault has produced a very lovely fault propagation fold in a series of varved lake sediments that provide really great stratigraphic markers of deformation through here. The other thing that we found is that there's one colluvial wedge preserved at this site. That again, the radiocarbon from this wedge providing evidence for one earthquake at about 2,000 to 3,000 years before present. And again, this was work by a former PhD student, Nick Herchhausen, and that paper has just been submitted, so hopefully it will be coming out soon. Okay, so now I'm going to move to some of the other faults that we had initially targeted as part of our survey. When choosing which of these faults we thought were active, first we were looking for inherited fault structures that we thought might have a chance to be reactivated, and specifically looking at the topography, looking for large topographic breaks or topographic expressions that would suggest to us and others that these faults might be active today. And 2 of those fault segments included the San Juan Fault and the western part of the Leech River Fault. But for both of these, what we've been finding is counter to what we thought we were going to find in the field. And so first, for the San Juan Fault, we're basically finding evidence that it was an Eocene left lateral fault. And so again, kinematic inversions of slick-sided fault planes show that they're consistent with left lateral slip along a steep brittle fault, but there's no major offset of any Oligocene to Eocene sediments. And it lacks any clear offset of Quaternary sediments. And so this suggests to us that either it's not active at all, or if it is active, it's experiencing such a slow slip rate that we're not preserving scarps, or it's not producing any sort of signature in the past 10,000 years, basically since deglaciation, which is our stratigraphic time record that we have to work with on this island. Similarly, on the western part of the Leech River Fault, again, this was documented by a former PhD student, Caroline Saylor, to be an Eocene subduction thrust. But similarly, it lacks clear tectonic offset of Quaternary sediments. So again, this suggests to us that, again, either it's not active or it's slipping with a relatively slow slip rate, and the scarps are not well preserved. Okay, so to summarize this part one of where are the active faults on Vancouver Island, we've got a slightly different base map here now, but this is still the Olympic Peninsula, Seattle, Vancouver, Victoria. The browns here are the basalts of the Matosin or Silesia terrains. The greens are basalts and other rocks of Regalla, the Regalla terrain. And what we've been finding is that it's basically these northwest to southeast striking segments of inherited faults, at least on Vancouver Island, that appear to be the ones that are active. And these faults that we're identifying in the field appear to accommodate both right lateral and a vertical component of slip. Normal slip here on the Beaufort Range fault, and thrust sense motion on the Leech River and Elk Lake faults. And also then what we're finding is that these east-west trending segments of inherited faults, like the San Juan and the Western Leech River, appear not to be active. Okay, so now this takes us to the second half of my talk, where we want to start thinking about, okay, what is actually driving the deformation in this northern part of the Forearc and Cascadia? So to think about this, I've kind of broken it down into two sub-questions. The first question is, which of these inherited faults that, these pre-existing bedrock faults on the island are actually oriented to fail in what we know about the modern stress regime in the Forearc of northern Cascadia? And in part B, we want to ask, well, is slip along these active faults driven by plate interface coupling, by the deformation that's happening outboard along the plate interface between the Juan de Fuca and the overriding plate, driving deformation in the overriding plate? And so to answer these, for the first part, I've been working on more Coulomb modeling of faults, given their known geometries and what we know about the current stress field. And for part two, we've been doing boundary element modeling of tractions on upper plate faults imposed by deformation along the subduction interface. Okay, so for this first part, again, we're assuming more Coulomb failure criteria for a set of faults in the overriding plate. So just a quick review of what that means here. So we're now plotting faults and stress states in a more Coulomb space, where we have normal stresses on the x-axis and shear stresses on the y-axis. Our stress state in this diagram is shown by a circle, and the geometry of the fault is shown here by this blue line. The fault in this system will have a resolved normal stress and shear stress given by this point, and we can determine whether or not that resolved shear and normal stress is sufficient to cause failure in the rock if we know something about the failure criteria of that. So we have this red line here indicating our failure criteria given by a friction coefficient and cohesion value. And so basically we're solving for these intersections. It's a couple of steps more complicated than this, given what we're doing on Vancouver Island. One of these levels of complexity is that we actually have multiple failure criteria, because we're going to have a set of friction values and cohesion values for the fault planes themselves. But also we have to think about, we want to be able to fall on these potentially non-optimally oriented faults, but not actually break any new faults or any new fractures in the surrounding crust. So what we've been doing is modeling this with friction values based on what we know about the mineralogy and composition of the fault zones, as we've seen them in the field and from some XRD data of the mineralogy, and matching that with laboratory-based measurements of fault friction. And then using a second sort of Byerly property for the bulk failure of the surrounding crust. So the other thing we need to know is, what is the modern stress field today? And so this is some work by Natalie Beaufort showing these red arrows are showing the maximum horizontal compressive stresses in the Cascadia Forearc. So to get you oriented here, this is the trench. Here's the Olympic Mountains, Seattle, Vancouver, Victoria, and then Vancouver Island in here. One of the main patterns that you can see in here that they talk about is that our compressive stresses are basically perpendicular to the trench, closer to the trench, as might be expected if coupling along the subduction interface is actually driving the deformation in the overriding plate, but that stress field rotates and becomes more parallel to the trench as you get farther inboard. And so we use the stress data that Natalie Beaufort determined from inversions of earthquake focal mechanisms and actually use the trend and plunges of their sigma 1 and sigma 3 data from their data sets. And so we use these inputs to test the parameter space that would promote failure along existing faults without breaking new faults. And we're doing this based off of what we know, based on field, laboratory, or geophysical constraints about the fault geometries, about the stress field orientations, making some assumptions about differential stress magnitudes at depths of about 10 kilometers, ranging from 0 to about 350 megapascals. Some assumptions about friction coefficients, again, based on our observations of the rocks and laboratory measurements of similar rocks. And some assumptions of what the pore fluid pressure state is, ranging from a hydrostatic to a lithostatic condition. And we're basically solving this parameter space for a network of faults in this yellow box here and in this yellow box here, basically the faults that we've been working on in Vancouver Island, plus a set of faults that others have been working on in Washington State. Okay, so what are some of the key results of this modeling so far? What we're finding is that there are a large number of scenarios where failure along our North Olympic fault zone, Southern Whidbey Island fault zone, eastern part of Leech River, Holoc Elk Lake fault, the Beaufort Range fault, where these fault systems are promoted to have failure in a more Coulomb framework. And in fact, they're tens to hundreds of times more likely to fail on an existing fault plane than to break a new fault in the crust, given this whole big range of parameter space that we're exploring of possible stress conditions in the forearc. And so what we're finding is that this set of faults is actually nearly optimally oriented in this stress field, and they can fail at a pretty wide range of pore fluid pressures or frictions, and they don't really need very high differential stresses. So these are all very reasonable conditions in the crust. So it's very reasonable to suspect that these stress state conditions might be met in the crust over periods of time. And if we use these more Coulomb predictions, they will predict that these faults are both active, but that they have a right lateral slip component. And these predictions from these more Coulomb models are matching what we're observing from the field. Each of these faults in these yellow boxes here are places where we know that they have had earthquakes, either because of our own paleoseismic work on Vancouver Island or because of other data from Washington State. And again, all of these systems have slip with a right lateral component, similar to what we would predict from the modern stress field. Now, if we look at, there's another set of faults, the San Juan Fault, the western part of Leech River Fault, and the Darrington Devils Mountain Fault. And in our more Coulomb simulations, these have very limited possibilities for failure. These faults are actually poorly oriented in the current stress field for failure. And they can fail, but it actually requires really, 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 really weak faults. And it's actually way more likely for the stress conditions in these areas to actually meet conditions where they would break a brand new fault in the surrounding crust that may be more optimally oriented than to try and fail on one of these existing faults. And again, this is matching what I think we're seeing from our field observations. The San Juan Fault and the Western Leech River Fault, from what we have seen, do not have evidence for Holocene activity. And others working on the Darrington Devils Mountain Fault, its activity is debated, but what is known about it is that it's relatively slow. Okay, so to summarize this part of the more Coulomb modeling, again, what we're finding is that these northwest southeast striking faults are well oriented for failure in the upper plate stress field. And these more Coulomb model predictions are matching our field observations for both their likelihood of being active and their slip sense. Whereas these east-west striking faults are not well oriented for failure, and we are not seeing strong evidence for recent activity along many of these faults. So finally, then we want to think about this potential role of deformation being driven by coupling along the plate interface, especially thinking about that change in the stress field that is visible with the Natalie Balfour horizontal stress field data. And so this is work, again, by PhD student Nick Hershausen, who used some boundary element models written by Jack Loveless and Brendan Mead, where basically you take the subduction interface of the Cascadia subduction zone. So again, to get you oriented, here's the trench. This mesh here is outlining basically the seismogenic portion of the Cascadia subduction interface. And these colors here are representing tractions on the plate boundary interface that they model based on geodetic coupling models. So basically, these are the stresses imposed at the plate interface that then get translated to the overriding plate. The model assumes the overriding plate is an elastic medium, and it basically transmits these stresses through the overriding plate to our set of receiver faults, same set of faults that I've been talking to you about so far. And basically, the idea is that it resolves these tractions on these receiver faults and is determining, what would be the kinematics and or magnitude of slip required to relieve that imposed stress. So that's kind of the quick and dirty of Nick's models. And so what are some of the predictions of his models? So these boundary element models predict that for this set of faults in North Cascadia, they should experience reverse slip if the faults are north to northeastward dipping, and little to no dip slip on near vertically dipping faults. How does this match with what we're seeing in the field? Well, we are seeing reverse slip on the Leech River and Elk Lake faults. The Leech River is pretty near vertical. The Elk Lake has a more moderate dip. So that's somewhat compatible, but we are finding pretty extensive evidence for normal slip, extension, and transtension along the Beaufort Range fault, which is it contradicts the compression that would be predicted from these plate boundary tractions. But more importantly, what comes out of looking at the strike slip component of deformation. Because these models are predicting that all of these faults in the Northern Cascadia Forearc should be experiencing left lateral slip. And that is the opposite of what we're seeing in the field. We're seeing evidence for right lateral slip consistently on all of our fault systems. And so what this suggests to us is that while plate interface tractions may explain some of the dip slip component of active deformation, that these plate interface tractions alone cannot explain the strike slip component of active deformation. So this implies to us that the observed upper plate deformation in Northern Cascadia cannot solely be driven by plate coupling. It's actually really interesting. And instead, it implies that the upper plate stress and deformation fields might instead be largely driven by far field plate motions or other upper plate processes. And so what kind of process may be driving this? There are a couple of models that might be applicable here. One is this model here on the left, where we've got northward motion of Forearc blocks in Oregon and Washington, driven by this large counterclockwise motion, geodetic motion that's been measured in the Western US, and these shear tractions based on the sort of the right lateral oblique slip of the Juan de Fuca subduction zone. And in this model, this northward motion of these Forearc blocks is now causing deformation at the northern boundary of the Olympic Mountains. These models do not allow for or do not predict deformation on Vancouver Island, where we are seeing deformation, and they're largely predicting thrust sense displacement on the Leech River Fault when I think we are seeing a component of right lateral. An alternate model that we've been considering is an active oroclinal bending model. So in this model, the idea, again, here we've got our trench and the Olympic Mountains. Here, if you look at the vertical axis rotations from the GPS field, you see this switch from this very well documented clockwise rotation of the Southern Cascadia Forearc, and it switches directions to counterclockwise north of the bend in the Juan de Fuca slab and north of the Olympic Mountains, and this bend in the Cascadia subduction zone. And that change in GPS-derived rotations matches a change in rotations shown here in black and gray in the paleomagnetic data. And so we've interpreted the system as an actively bending orocline, and in that sort of model would predict a right lateral sort of slip sense. You can think of it like a flexural slip type model. Along these faults, you would expect compression in the core of your hinge and extension along the limb. So this might be a model that is actually better explaining our observation. Okay, so to summarize the whole talk here, our group has been working in the field to provide evidence for numerous active faults on Vancouver Island. We've documented the activity of the eastern portion of the Leech River, the Holoc Elk Lake Fault, and the Beaufort Range faults. Each of these faults have between 1 and 5 earthquakes recorded in paleoseismic trenches that range from the late Pleistocene to Holocene, the time scale of the Quaternary deposits that are available on this island. And from our field observations, it suggests that deformation and our modeling, it suggests that deformation may only reactivate portions of older inherited faults that happen to have favorable orientations, given today's effective stress conditions. They might be opportunistically using portions of them and opportunistically making their own in other locations where that is actually the better option. And our models of thinking about what could be driving upper plate deformation suggests that plate coupling is not the only mechanism driving Forearc deformation here in northern Cascadia, and that these far field plate boundary tractions or oroclinal Forearc bending likely play an important role. And so with that, I will end and see you.